So welcome to my talk, and this is my first time ever in India, and I'm very lucky to be here in Goa. This talks about how we can build advanced security application on top of emulator framework named Qiling, and you can find the Qiling website at restqiling.io. So a bit about myself. My name is Nguyen and Quynh, and I'm working in Nanyang Technological University in Singapore. And I'm doing research, and mostly in low-level stuff like operating system, virtual machine. And in the last few years, I spent a lot of time working on binary analysis. And I happen to be the author and the maintainer of few reversing frameworks like Capstone Disassembler, Unicorn Emulator, and Keystone Assembler. So I have my this talk has another co-speaker named Qiling, but unfortunately he cannot travel because he's in China now. And the Chile team has a few other very good researchers like Delay, Witcher, Known, Spiker, and Kabel, but sorry that they are all from China and they cannot travel, so it's only me here today. So in this talk, I spent some time on the motivation, the background of why you have been doing this. And after that, we look a bit at the shellcode emulation, which is the first ever version of Qiling. And after that, we see how we design and implement Qiling frameworks. And next, we see how we can quickly build some dynamic analysis tools on top of Qiling framework. And we have few demos. We have live demo, we have recorded demo in videos. Okay, a bit about background of this research. So about 5 years ago, in 2015, I built Unicorn framework, which is emulator framework, and we released it first time in Black Hat USA, 2015. And Unicorn is basically a multi-CPU, multi-platforms framework. So it allows you to emulate CPU instruction. And we support different kind of CPU architectures. We can emulate Intel, ARM, ARM64, Mips, Spark, and M68K. And we run cross-platform, which means Unicorn can emulate all of those CPU instructions on every operating system that you can find, like Windows, Linux, Mac, and so on. Unicorn is designed to be very simple and very easy to use. And the most important thing about Unicorn that make it widely adopted by a lot of research and products is that it supports fine-grained instrumentation. So when you emulate the CPU instruction, you can put the instrumentation at many levels. You can put it anywhere in the code. You can instrument every memory access. So here's one very quick example. So suppose that we want to emulate these 2 bytes. Okay, these 2 bytes, 41 and 48, which is increased ECX and decreased EDX in Intel 32-bit. So the way you can use Unicorn to emulate these 2 bytes is that you specify the address where you want to emulate these 2 bytes. And after that, we initialize the Unicorn engine. So here, we say that we want to emulate Intel 32-bit, right? And after that, emulator needs some memory. So before you do anything, we map the memory into the virtual machine, into the emulator. So in this slide, it's very confusing. Okay, in this slide you can see that I map 2 bytes into the memory after I initialize the UNICORN engine. And next, I write these 2 bytes. Sorry, is it any laser pointer here? Do you have any laser pointer? Okay, in the next slide, you can see that I copy 2 bytes into the memory at the address I specify here, right? And after that, we have engine, we have memory, we have instructions that we want to emulate inside the memory. And now before we run the emulation, we initialize the CPU context. So in this case, I initialize the 2 registers, ECX and EDX. It will be 1, 2, 3, 4, and 7, 8, 9, 0. And after that, in the next slide, I run the emulation. I say that, okay, I emulate from that address and only 2 bytes, right? And after that, emu start, come back, the emulation is done. Okay. Okay, we are done with emulation here. And after that, we see the result of the emulation. And here I get the updated CPU context out and print out. So what happened here is that I set the value for ECX and EDX here, and when emulation, I increase ECX by 1 and decrease EDX by 1 and run the emulation. So here's a quick demo of this code. So see, here is the code, and now I will run it. Oh, why does it work? How can I switch? Oh, I see. Okay, here's the code, right? And now I run this one. The shape that I just show you. You see here, after emulation, ECX is 1, 2, 3, 5, right? Which is expected because we add 1 to ECX, and EDX we subtract 1 from that, so EDX become 7, 8, 8, F. So that's how the UNICORN works. So, however, there are some limitation of UNICORN. You can see that UNICORN only emulates the low-level instructions and some memory access and that's all. UNICORN cannot know or is not aware about higher-level concept of operating system, only low-level concept, right? So it doesn't know about file format. It doesn't know library. It doesn't know about file system. It doesn't know about system code. It doesn't know about operating system that can run on top of that. So what you can do with UNICORN is that emulate some raw instruction and memory set and that's it. No higher level concept. Okay, so we think that we can do better. And that is how we started Qiling. Qiling is to fix the limitation of UNICORN. We introduce higher level concept on top of UNICORN and make it Qiling. And thanks to that, Qiling understand higher level concept of operating system. So not only emulate low level instructions, but we can understand how understand what the code does when it runs. So the first version of Qiling, we just simply made a shellcode emulator. So you know that shellcode is a very important step in exploitation, right? So we find some bugs in some software. Usually you introduce some special input that can trigger the bugs. And when the bug is triggered, we run the shellcode. So on the other side, as a defender, if we somehow get some vulnerabilities, we want to understand what the shellcode does. So somehow, if we can extract out the shellcode from the exploitation, we need to understand what this shellcode does. And unfortunately, shellcode is getting more and more complicated, and it's not easy to understand how it works inside. So a good way to understand how shellcode works is to emulate it somehow. And there's some good solution for this kind of problems, like NULLCON. NULLCON is one open source, very good project. This one is also built on top of NULLCON emulator. And you can use NULLCON to emulate shellcode, but NULLCON has some limitation that I can introduce that. I will introduce that later. So the question is that you want to understand shellcode, but the shellcode can come from different CPU architectures. Shellcode can be for Mips, can be for ARM, can be for ARM64, can be for Intel, and shellcode can be for different operating systems. Shellcode can be for Windows, for Mac, for Linux, for BSD, and so on. So our emulator, shellcode emulator, need to be able to support all kinds of these operating systems. And it needs to be able to understand all the CPU instructions of those shellcode as well. So one way to understand the shellcode is that we emulate it, and the extreme way is to have some full virtual machine, and somehow we run the shellcode inside the full virtual machine and understand how it works. We try to analyze it when the shellcode runs inside the virtual machine, but we think that is a bit too much, a bit too overkill, and we want something more simple, more lightweight. And actually, you can find some existing shellcode emulator out there in public, available open source. And we look at them and we found them to be to have many issues. First of all, you get somehow how you get a shellcode that you want to analyze. But the shellcode can come in different format. It can be in binary format. It can be in source code, which is in assembly format, or it can be hex format. So the emulator need to be able to understand all of those formats. And in case the shellcode is in assembly, you need to be able to compile the assembly to get back the binary before you can really emulate it, right? So that's one issue. We need to have an assembler that support all kind of CPU architectures. And yeah, we found something like that, but it's those existing emulator for shellcode are complicated, doesn't support many kind of CPUs, or doesn't support many kind of operating system, and the functionality is quite limited. So we built our first version of Qiling, and we name it Qiling. And you can see here's how the Qiling works. So as the input, we have the shellcode as the input. The shellcode can be in the assembly format. It can be in binary. It can be in hex format. And in case the input is not binary, we use our own assembler framework. And in this case, we use Keystone assembler. We compile the assembly shellcode, and you get back the binary. And after that, we perform some pre-processing, and we initialize our emulator, and we inject the shellcode into the emulator. And inside the emulator, you support different kinds of CPUs. And actually, here the emulator is built on top of NULLCON, so we support different kinds of CPUs like ARM, ARM64, Mips, Spark, and Mips, and M68K. Moreover, shellcode emulator also support different kind of operating system. The reason is that the shellcode can execute some system code. And to be able to understand that, our emulator need to be able to understand the system code, how it works inside, so we can emulate it properly, right? So the core here, we emulate the CPU instruction, we emulate the system code, and the emulator run, and when it run, we can monitor the behavior, and you can log, you can dump, you can write out on the activities that the shellcode does inside. So here is some demo for this. Can you see that? Okay, in this case, I have one shellcode for ARM64. And remember that my machine is Intel, right? We cannot easily, typically, we cannot run ARM64 code on this one. But thanks to the emulator, we can do that. So Qiling has a tool named QL tool. And here I will run QL tool. QL tool it takes as the input the shellcode. And in this case, the shellcode format is in hex format. And we tell the QL tool that we want to emulate this shellcode as a shellcode coming from the Linux operating system. And this one uses ARM64 instructions. Okay? So we run this. Okay, you see here how Qiling emulates the shellcode from ARM64. So we just dump out high-level information. You can see that this shellcode open the socket and try to connect to the local REST. It's only for demo. And it duplicates some file descriptor. And finally, it executes some binary. And in this case, this shellcode try to execute shell on the target machine. So you can run also, in the case you want to see more information, you can tell Qiling that you want to get more details. Okay, I specify the output as disassembly. So it when it tries to emulate the shellcode, it dump out on the instruction that shellcode executed. And that is Linux shellcode. We have another demo for, okay, this one for Windows shellcode. So very similarly, I run I have the Windows shellcode as the input and I run QL2 on that. Let's see what happened. You can see that it's a bit slower because Windows need more emulation. We need to emulate operating system. We need to emulate the operating system structure inside the memory. And we does many kind of things behind. And you can see that this shellcode execute in exec function, execute get version, is another Windows API. After that, it execute exit process. So yeah, here is the high level summarize what this shellcode does. Okay, get back to our talk. Yeah, we can support. Qiling can emulate shellcode from Windows, from Linux, from BSD, from MacOS, and for different kinds of CPUs, ARM64, Mips, Intel, and some others. So after the first version of Qiling, we thought that we can do better, because shellcode which means very simple code, and you can do a lot better. So how about emulate the full binary, the full program, not only the shellcode usually with very little context. So we went on and extended the first version of Qiling to make it a full emulator that can emulate the full binaries coming from different OS, from different CPUs. So here you can see the features of Qiling. It's a cross-platform, cross-architectures, and we support multiple file formats because the programs that you want to emulate can be from Windows, which is PE format. It can be from Linux or BSD, which is EUF format, or it can come from macOS or even iOS, and that is a match of format. So Qiling is able to emulate the full binary, and it also create a sandbox for that process. So we have the emulation running in an isolated environment. We provide high-level API to set up and configure the sandbox. And thanks to the lower-level NULLCON emulator, Qiling provides many kind of instrumentation at various level. We can instrument at instruction level, basic block level, memory access, exception, system call, and so on. Qiling allows you to dynamic patch the program on the fly, which means when the program runs the program, you can patch the emulated program inside the memory. And Qiling this one is very important. We choose Python as a programming language. So Qiling is a Python framework. Make it easy for you to build the customized tools on top of that. And recently you have new features. We embed ZDB server inside the Qiling, so we can turn it on at the runtime, and not only you analyze it, you can debug it. That opens many possibilities. Okay, so at the time we design and we look at Qiling features, we look at existing solution. And okay, we list here a few solutions, and most of them are open source. You can see that many of them are not cross-platform, which means they run on only some limited operating system, or they are not cross-CPU, which is some of them are only for Intel, right? And some of them do not support instrumentation, which means you cannot really build your analysis tools on top of this. And some other are not really tools, are not really frameworks, like QEMU is a mode that can emulate many things, but it's not a framework, it's a tool, which means you cannot build your own tools on top. So we design Qiling to fix all of them, to be multiple CPU, to be multiple platforms, support instrumentation, easy to build tools on top, and some other things. So there are some issues we need to consider when we build Qiling. So we look at some existing emulators at that time, and two of them are QEMU Isomode and UserCon. And these two emulators are quite good, but there are some limitations. And here we want to emphasize on system call forwarding. So here is why we need to do this. So, okay, suppose that you have the program you want to emulate, right? This program, at some time, we execute some system call to request some information from the operating system, which means our emulator need to emulate the system call, right? So the way QEMU Isomode and UserCon handle system call is that they do not really emulate system call, but they take the request from the program and they forward the request to the host operating system. And thus, after that, the host returns the system call result, and the emulator returns back the result to the program. So you can see here that for these tools, they operate as a proxy between the program and host OS. And that's how they can support many binaries. So the problem here is that if you do that, the emulator, the code you try to emulate, and the host must be able to be in the same OS, right? So you can only emulate Linux program or Linux host. You cannot emulate Windows program or Linux host, because Linux host doesn't understand Windows system code. So Qiling tried to fix it. Here is a full diagram, which is quite similar to the shellcode emulator. You can see the difference is, as the input is not only raw shellcode, but we support a full program. So as the input, you can see that we have Linux binary, BSD binary, we have Windows binary, we have Windows. Here's Windows 64-bit. We have MacOS binary. So emulator Qiling will take all of these kind of programs in as the input, and inside the emulator, it tries to load this program into the memory and do all kind of setup. And after that, internally we try to this step is quite similar. We emulate all the operating system that we try to support, like Windows, Linux, Mac, and BSD. Because the program can execute some high-level libraries. So, in addition to only emulate the low-level instructions, we need to be able to support higher-level concepts like API and system code, right? And after that, we emulate the binary, and as the output, we can summarize the behaviors of the input program. So that is the idea, but it's not easy to implement the idea. So there are many things that we need to show in our adventure to reach our target. So here you can see that Qiling need to be able to load the program into the memory. And the program, the input program can be different kind of format. It can be EAF, it can be PE, it can be MacOS. So our emulator need to be able to understand all of this format. And what we did is that first we need to have parser for every kind of format. We have parser for EAF, we have parser for PE, we have parser for MacOS. And after that, after parsing step, we need to load all of these sections of all of these binaries into the memory properly. And here we do exactly as a original operating system does. The next step is how to emulate system code. So here maybe the screen is a bit too small, but I can explain how we do. So first of all, here we want to emulate read system code, right? So inside the emulator, we check the FD of the system code to see that the file that we want to read already open or not. If it's already open, then we try to detect that if the FD is from socket or from normal file. And after that, we read the content of the file into the buffer, and after that, we return the buffer to the program. That was for POSIX OS. For Windows, it's a bit different. Windows is not much about system code, because usually normal program is just execute some high-level API, right? And those high-level API, they access to many different structures inside the Windows memory. And you can see that here are some structures that all program access to in the memory, like TEB structure, PEB structure. And Qiling need to be able to emulate all kind of these structures into the memory. We generate the requested structure and copy it into the memory of the emulator, like the program expected. Okay, here's another thing. Because the Windows program can, when you run it, access to many double linked lists. into the memory, like the list of imported DLL, imported function, exported function. So internally, Qiling need to emulate all of those double linked lists as well. CPU is not easy. So at a lower level, before you run the program, you need to initialize the CPU properly. Otherwise, program cannot run. So here, for example, on the Linux program, macOS program, or Windows program, when they run, they access to some segments into the memory, and Qiling need to set up on them. Otherwise, program doesn't work. And there's some other things we need to do for different kinds of CPUs. For example, Arm64, they need to have some special kernel initialization, for example, for TOS or for float pointer. So Qiling had to handle that inside the core as well. Here, same for Mips. When we implemented Qiling for Mips, we found that, okay, Mips need coprocessor. And without coprocessor, you cannot run the program. So for this, actually, you had to patch NULLCON. So NULLCON can support coprocessor for Qiling to work. Okay, here comes some demo. Okay, you can see that here's one simple example. You can see how to build your own tools on top of Qiling. So Qiling inside it already takes the responsibility to load the binary into the memory for you. And Qiling also provided a system call and system API and logging capability as well. You can turn it on by default. And if for very basic application, you do not really need to do anything. So here's one example. You can see that. I want to emulate this binary, ARM, right? On Linux. So what I need to do is that I just need to import Qiling first. This code is Python, right? And after that, I initialize Qiling engine. I tell Qiling that I want to emulate this program. And here's the root FS of this program. And this one is Linux. And we emulate it in debug mode, which means at runtime it print out many information. So I will run this demo for you. Okay, you can see that I try to run this script in default mode, so it doesn't print out too much information. Can you see that from behind? Okay, now I try to run this one. So this program is a very simple hello world program. It does something before, and after that it write to the write hello world to the console. That's it. If we turn on the debug mode, you just tell that Qiling that okay, I want more information here. So like just okay, I turn on disassembly mode. So when we emulate the program, it print out on the assembly instruction. Okay, and now that's a very basic program that you can view on Qiling. But we can do a lot more. Because Qiling allows you to instrument anywhere. So, after you initialize the engine, here, you can set up the callback. So, in this case, I use a hook code API to set up the callback. And hook code will execute the callback at every instruction. And in this case, I print out the instruction at that location. And if you run this one, you see exactly the same thing as the last demo. It executes, it emulates the binary, but after every instruction, it executes the callback, and this callback print out something. But of course, in your more advanced program, you can do something more advanced in your callback. Okay, here's one very nice application for Qiling, firmware analysis. So why Qiling is very useful for analyzing firmware? The reason is that by emulation, you can move the analysis to much more powerful platform, right? So like you want to analyze the ARM binary, you do not need to run that on the ARM device, but we emulate on much more powerful Intel machine, right? The second reason is that usually talking about firmware analysis, you do not really want to analyze a full firmware, but only one small binary in that. And Qiling is useful because you can take that binary out from the firmware and emulate that inside Qiling. Yeah, there are many challenges if you want to do that, but anyway, that's the idea. Recently, some researcher try to use Qiling for fuzzing, and he built a guided fuzzer using Qiling. The reason is that Qiling allows instrumentation, so you can do own cap instrumentation inside the fuzzer, and instrumentation is very important for guided fuzzer, right? So yeah, you can look at the link and see that how he built the guided fuzzer using Qiling, and it works for own cap binaries and CPUs. Qiling is also very useful for analyzing the malware, right? Because you can see that when you emulate the binary inside the Qiling sandbox, you can contain the binary, the malware behavior. And because Qiling works cross-platform, that means you can emulate the Windows malware on Linux, which is very nice. And because Qiling provides API logging capabilities, so you just need to turn it on, and that's it. Very easy and simple. And Qiling will, by default, can automatically summarize the behavior of the malware for you. Finally, we have a nice feature in which we embed the GDB server inside the Qiling emulator. You can turn it on just by a single line of code, ql.gdb to true, and after that it's on at localhost port 9999. So when you analyze the binary, you can use your familiar GDB client to analyze the binary running inside Qiling. And because IDA Pro support GDB, so you can also use IDA Pro to analyze the program running inside the Qiling emulator. Okay, here comes my conclusion. Qiling is a Python lightweight emulator framework. We try to emulate what we need, and we ignore everything else. So that makes it very, very simple and very lightweight. It has a built-in shellcode emulator, but better than that, you can emulate the full binary. And Qiling is well maintained by a good team of researchers. We are dedicated to maintain and to keep this running for a long time, and we keep adding more and more features. And we plan to release the first version 1.0 very soon. And you can expect more exciting binary analysis tool on top of Qiling built by us. or hopefully from community in the near future. So here's our website, our GitHub, and if you like the project, you want to show your support, please come, check it out, try it, and give it a star. We need more star. We have like close to 600 now, but we need more and more. Finally, we want to call for sponsor for development of NULLCON 2. You know that current NULLCON version is based on a very old QEMU version, 2.1.2 from like 5 years ago. And we did not really update it after that. So we plan to build the next version of NULLCON 2 based on a newer QEMU, the latest QEMU version. So have many bug fixed, many new features, faster, and yeah, a lot more advanced. And probably you can add some more CPU architectures in the NULLCON 2 as well. But yeah, we need some sponsor to make this work because it's a lot of time and effort. Otherwise, yeah, I think it's very hard to make that happen. Okay, you can see my email at the bottom. You can contact me if you have any ideas to how to improve our Qiling framework, or you want to support our works, its own open source. Yeah, I'm done. Any question? Sorry that I'm running out of time, but yeah, actually I prepared quite a lot of very nice demo, but I had no time to play them. But you can check it out the homepage of Qiling website. We put all the demo, all the recorded video on YouTube, and you can see that from our website.
Any questions?
Yes.
Thank you for the excellent talk, Dr. Nguyen. You said that one of the use cases was malware analysis. So
yes.
In case it is a multi-staged malware with multiple files being dropped one after the other, so will it be possible to emulate that in Qiling's present form, or is it just one binary at a time as of now?
Can you repeat the later part? Can you what?
Yeah, sure. So as of now, yes, can it process multiple binaries, like in case of an advanced malware which drops multiple, EXEs, multi-stage?
Yes. Qiling can emulate Windows binary. Yes.
Yes, Windows binaries. But what if the malware is a multi-stage dropper? Which drops 2 EXEs at one time, one after the other.
Okay, that is beyond the scope of this one, right? This one gives you a framework. And for those more complicated, we do not do that.
Understood.
Right? Yeah. Okay. Frameworks mean you can build your tools on top. For those more advanced, more complicated, and very, special like that, you need to build that yourself.
Thank you. Thank you so much.
Yes.
Any other question?
No more question?
Thanks, sir, for the session.
Thank you so much. You can always find my contact me on either Twitter or email. Yeah. Thank you so much.